All right, let's jump right into this explainer. Today, we're tackling a massive part of CS 217 object-oriented programming. We're zeroing in on class relationships in C++, how we manage inheritance, how we lock down our code using specific identifiers, and how we actually safely navigate our object hierarchies using downcasting. Honestly, if you've ever spent hours hunting down a bug only to realize you slightly mistyped a function parameter in a derived class, you are in exactly the right place.
Here's our roadmap for the day. We're going to cover the overriding problem, the override identifier, the final keyword, an intro to downcasting, the dynamic cast operator, and wrap up with some key takeaways. Okay, Section 1, the overriding problem and how we actually secure our inheritance.
So here's the absolutely crucial point. To actually override an inherited virtual function, your derived class has to be an exact match. I mean, exact same return type, exact same name, and exact same parameters. It's a strict is-a relationship. If you deviate even a tiny bit, you're not overriding anymore. You've just accidentally created a brand new function. And trust me, that leads to an absolute nightmare when you're trying to debug later on.
This really brings us to the ultimate showdown, right? The compiler versus the programmer. Because if you make a mistake, say you tweak a parameter but you think you're overriding, your code might actually still run. But it's going to generate these silent, sneaky, logical errors where the base function fires when you totally expected the derived one to. What we absolutely always want to do in object-oriented programming is force those invisible bugs into loud, screaming compiler errors. We want the build to just stop dead so we can fix it right then and there.
Moving right along, Section 2, using the override identifier, or as I like to call it, making the compiler your best friend.
Picture a classic A to B to C hierarchy. We've got base class A, B inherits from A, and C inherits from B. Now check out what's happening in class B's code. We have this virtual print function, but we slap the word override right at the very end of the function header. Doing this explicitly states our intent. We are literally telling the compiler, hey, I am trying to override a base class function here, so check my work.
Now definitely pay close attention to this because it's super vital for your exams. In class C, the base class function returns void. But if we mess up and write int print override, that override keyword is going to trigger an immediate compile time error. Without it, the compiler would just silently create a new int returning function and ruin your day. But because we've forced it to check, it stops and basically says, nope, your return types don't match.
And here's a brilliantly sneaky edge case. What if we change the header to add const, right? Like void print const override. Well, if the base class didn't have that const qualifier, the whole match is broken. It fundamentally changes the signature so it's not an override anymore. Once again, our trusty identifier catches it instantly, throwing another compile time error.
All right, Section 3, the final keyword and how we put a hard stop on inheritance. You know, sometimes you build a class or a function and it's just perfect, exactly as it is. You don't want anyone tweaking it further down the line. So here are the core rules for final. First off, stick it at the end of a function header and bam, no derived class can ever override it. Second, you can declare a whole class as final, which completely shuts down inheritance. Literally no one can derive from it. And third, just like with override, if someone tries to break these rules, the compiler throws a hard error and stops the build cold.
Okay, let's pivot to Section 4, an intro to downcasting, where we navigate these class hierarchies.
So, upcasting is a breeze, right? A derived object literally is a base object. Easy. But downcasting? That's converting a base class pointer down into a derived class pointer, and that creates a very strict logical boundary. This conversion is only, and I mean absolutely only, valid if that base class pointer was already secretly pointing to a derived class object in memory. If it's just pointing to a standard base object and you try to force it down, yeah, your program is going to crash hard trying to access data that simply isn't there.
Which perfectly tees up Section 5, the dynamic cast operator, our tool for safe downcasting.
Say hello to dynamic cast. This is incredibly relevant for your assignment, so definitely lock this in. Unlike our identifiers that do their thing at compile time, dynamic cast goes to work at runtime. It actually inspects the object in memory while your code is executing. If the object isn't actually the right derived type, it safely returns a 0 or a null pointer instead of totally crashing your program. But, and this is a big but, you've got to remember the limitations. It will outright fail if you use protected or private inheritance, and crucially, it completely fails if your classes don't have any virtual functions at all. It actually relies on the virtual table to figure out the object's true type at runtime.
Let's wrap things up with Section 6, Key Takeaways and Rules for Your Exam Prep.
All right, these 4 points are your golden rules for keeping C++ object-oriented code safe and predictable. Number 1, overriding requires exact matches across the board. Return type, name, parameters, all of it. Number 2, always use override and final to turn those silent, terrifying logical errors into loud compiler errors. Number 3, downcasting is how you access derived specific data. And number 4, dynamic underscore cast is the safe way to pull that off. Just remember, it demands public inheritance and at least one virtual function to actually work.
So, I'm going to leave you with this thought. If the compiler is smart enough to catch our inheritance mistakes with just a couple of explicit keywords, how else can we structure our future code to force the compiler to act as our ultimate safety net? Remember, the best programmers don't just write code that works, they write code that outright refuses to compile when it's broken. Keep that mindset for your next assignment. Thanks for hanging out with me for this explainer, and happy coding.